Hey boys and girls, welcome to 5.6. This one is called Solving Inequalities in Two Variables by Graphing. Way back in chapter 2, this would have been in October, we learned how to graph inequalities on a number line. So for example, if you had something like x was greater than 4, you knew to put a point at 4 and draw a line to the right. But when we did that, that was only using one variable inequalities. When we have two variable inequalities, we're actually going to be using the coordinate plane, graphing an entire line, and then using a shading technique to determine the solutions to an inequality. So whereas equations, when we solve the systems of equations by graphing, when the lines intersect, they only had one solution. Well, when we graph inequalities, you're going to find that there are an infinite number of solutions that work, but they're either going to be above the line or below the line. And so our topic today is graphing two variable inequalities, and we're trying to figure out how do we solve inequalities in two variables by graphing. So when you see the inequalities, you're going to see these symbols, which we've used before. We have that one or that one. And if you remember, we always read it from left to right. This is less than, and this one is greater than. Now, in addition to those, they're not different necessarily, but in addition to those, we will also see a symbol that looks like that, which if you again remember from chapter 2 is less than or equal to, and then the other version is greater than or equal to. So these are our four possible symbols that we are going to see. Less than and less than or equal to, or greater than and greater than or equal to. And then after we graph our line, the way that we're going to show our solution is by using a shaded area or boundary. So we're going to have a section of our graph that we shade in, and that will represent the solution to our two variable inequalities. Now when we draw the original line, it has two possibilities. It can either be a solid line or a dashed line. And when you have a solid line, that would only happen if you have a less than or equal to or greater than or equal to. And so any points on that solid line are solutions to the inequality that we're graphing. But if it's only a less than or only a greater than sign, you're going to draw a dashed line, and then any points on that dashed line are not solutions to the inequality. Now obviously right now you haven't seen any graphs yet, so this might not make a whole lot of sense, but once we go through a lot of the graphing examples, you'll understand, okay, what line do we do, a solid or dashed line, and that's going to be based on the sign, the inequality sign that we have, and then I'm going to show you how this shading occurs either above the line or below the line. So previously, when we graph lines, we became very familiar with the y equals mx plus b form. Many of the inequalities that we graph will also appear to be in that same form. The only difference is there's no equal sign right here. Instead, it's either going to be a less than or equal to, greater than, or greater than equal to sign. But for the sheer purpose of graphing the line, we're going to treat it as the y equals mx plus b version of the line. And the reason for that is so that we can still identify our y-intercept and we can still identify our slope to help us determine where those points on the line occur. So if we were to take y equals 1/3 x minus 3, we know that this minus 3 right here is our y-intercept. So our y-intercept is at 0, -3. And we're going to plot that point right here. There's 0, -3. And then if I notice that my slope is 1 in the numerator, 3 in the denominator, that means up 1, right 3, up 1, right 3. Okay? Now, as I do this, from this point that I already graphed, I go up 1, right 3, put another point, up 1, right 3, put another point. And now I ran out of room to put more points over here, but if I wanted to add more points, I can do the opposite, which is down 1, left 3, down 1, left 3. Now, I don't want to just connect the points yet. I have to recognize, well, what inequality sign was I using? And so this one was less than or equal to. Okay? Well, when you have a less than or equal to or a greater than or equal to, it's going to be a solid line. If it was only less than or only greater than, that's going to be a dashed line. Well, again, if I look at the symbol that I started with, this was a less than or equal, and I'll write it in just so we remember. Less than or equal to. That means I can connect my points with a solid line. Okay? You want to use a ruler for this. And there's my line. Okay? So now, we have to determine, well, where are all the numbers that actually make this inequality true? So what I'm determining is, where do I shade the entire graph? And here's what that means. Here you have your inequality, and you have all this region of the graph that's above the line, and then you have all this region of the graph that is below the line. We're going to shade one of them. We're either going to shade everything above the line or everything below the line. Well, that means we have to test one of the points on the graph. Okay? And we don't want to pick a point that's on the line that we drew. We want to pick a point either somewhere up here or somewhere down here. And it can be any point you want. Okay, so we need to pick a point. We're going to test a point that is not on the line. And then here's a very important hint. If we can, the easiest point to test is 0, 0. It makes the math the easiest to do. Well, 0, 0 is right here, and it's not on the line, so I can use this point right here to test. And all that means is, I'm going to test 0 for the x and 0 for the y and see if it makes the inequality true. So I'm going to rewrite our original inequality down here, which was y is less than or equal to 1/3 x minus 3. But now what I'm doing is I'm replacing this y right here with 0, and I'm replacing this x right here with 0, and I'm trying to see if it makes the inequality true or not. So it's going to be 0 is less than or equal to 1/3 times 0 minus 3. So all I did was replace this y and this x with the 0, 0 point. And I'm trying to decide, is this inequality true? Well, I have 0 on the left. This 1/3 times 0 is just 0, and I have minus 3. That leaves me with 0 on the left. 0 minus 3 on the right gives me negative 3. Now look at this inequality. Is this true or not? Is the number 0 less than or equal to the number negative 3? And the answer is no. That's a false statement. Now because that's a false statement, let's go back up to our graph. Look where 0, 0 is. 0, 0 did not work in the inequality. It didn't make the inequality true. So that means 0, 0 and any other point in this entire region up here doesn't work. But then what that does tell us is Everything below the line does work. So this, all of this area right here, is my solution. And by my solution, what that means is pick any point in this shaded area. Any single point you want, it will make this inequality true. So let's pick a really easy point. Let's pick, let's just randomly pick this one right here. So this point right here is at 0, 1, 2, 3, 4, 5. So 0, -5. And I'm going to plug that in to this inequality right here. So let's rewrite the inequality again. Y is less than 1/3 x minus 3. I'm going to replace y with -5 and x with 0. So it's going to be -5 less than or equal to 1/3 times 0, 0 for the x, minus 3. I'm going to determine if this is true. Well, -5 on the left, less than or equal to 1/3 times 0 is 0. I have minus 3. And then I have -5 is less than or equal to -3. Is -5 less than or equal to -3? Absolutely it is. That's true. And again, I could have picked any point in the shaded region and it would have made the inequality true. But if I would have picked any point up here to start with, it would have been false. I picked 0, 0 because 0, 0 is by far the easiest point to plug in for your x and y. It'll make the calculations the easiest to figure out. Okay? Now the other big takeaway from this is because it was less than or equal to, not only does all the shaded region qualify as solutions for the inequality, but any point on the line, because it was a solid line, any point on the line also works as a solution to this inequality. So there are millions and millions and millions of points that exist below this line. And if we extended our graph, we would just get more and more and more points below the line. Every single one of those points makes this inequality true. So the shaded region qualifies as the solutions to our two variable inequalities. Okay? All right, the next thing we're going to look at are the example questions. And we start with questions where all we're doing is plugging in the x and y value and seeing if they work. So remember, our first one is the x, and our second number is always the y. And all I'm going to do is plug in those numbers and see if they make my inequality true. So my x is 3, my y is 2, and I'm trying to determine, is the left side greater than the right side? Well, 3 plus 2 is 5. Is 5 greater than 5? No. I'm going to put an X to mean like on Family Feud, And so that doesn't work, so we would just say no, not a solution. Okay? Now I'm going to quickly show you 2, 3, and 4 as well. Alright, so for number 2, x is 5, y is 3. I plug them in for the x and y. And as I work it down, I notice that 2 is greater than or equal to 2. Yes, that works, therefore it is a solution. For number 3, x is -1, y is 2. I plug them in accordingly. Now when I do my math here, -1 plus 4 less than or equal to 4 is 3 less than or equal to 4. Yes, it is less than, so check mark, yes. And the last one, I plug in -1 for x. I plug in -1 for y. 3 times -1 is -3. -4 times -1 is +4. Is my left side greater than 6? The answer is no. 1 is not greater than 6, so it doesn't work, so that is not a solution for the inequality. So that's going to conclude kind of part 1 of this lesson. The next video will go through all the graphing and shading that you will need to know for the homework assignment. Okay, see you in the next video.